Now in this lecture we find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD equals to 3 units in its length. Inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units in its length. The radius of this small semicircle equals to 1 unit. And our mission is to find out the length of this line segment AE. So first of all, we know that all the angles in any rectangle are right angles. So those 4 angles, they're all right angles. So this is a right angle. This is also a right angle. This is a right angle, and this is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point P. We will define the center of this small semicircle. This point is point Q. We will define the touching point of those two semicircles. This point is point S. Likewise, we will define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we will define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we will extend line segment AE inside the DC of this rectangle ABCD by a straight line until they touch each other. This is their touching point. We will define this point, their touching point, as point F. So DC is one side of rectangle ABCD, and therefore it is absolutely a straight line. Then by doing the construction, we extended side DC. We extended the straight line DC by a straight line, and the result is DF. When you extend a straight line by a straight line, the result must be a straight line. So DF is a straight line. If we focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle, that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, by doing the construction, we created the right small triangle ECF. We define this angle EFC as alpha, and we will continue to focus on the small right triangle ECF. In the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the same rule that states that that the sum of the angles on one side of a straight line, and that the sum of the angles in any triangle is equal to 180 degrees. Okay, so here we have PD equals to PS, both the radii of this big semicircle, this is equal to 2, therefore each of those two line segments is equal to 2 units in its length. So I'll write it down. PD equals to 2, PS also equals to 2. Likewise, QS equals to QC. Now both the radii of this small semicircle, that is equal to 1. So QS equals to 1, and SC also, and QC also equals to 1. Here we have CF, line segment CF is unknown. We don't know what is the length of this line segment CF, so we will define the length of this line segment CF as x. So here we have the radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, you can implement rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB, that is tangent to this circle at this point, point M. In addition, we have also the radius OM, that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL, that is equals to 2. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius QG of this small semicircle is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in the right triangle, the right small triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that the right big triangle LPF is similar to the right small triangle GQF. So I'll write it down. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF. Is a big right triangle LFP, and it is equal to this angle. This is actually angle QGF. In a small right triangle FGQ. Look it again. Angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle GQF. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha, as it belongs to the small right triangle GQF, it will be defined as angle GFQ. So repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle LFP, and it is equal to this angle. This is actually angle GQF in the small right triangle FGQ. So repeat again. We actually found out that angle LPF in the big right triangle LPF equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the triangles in the big right triangle LPF are correspondingly equal to all the triangles in the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So I can find out that the right big triangle LPF is similar. This is the sign of similar to the right small triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP in the big right triangle LPF over side GQ in the small right triangle GFQ equals to side PF in the big right triangle LFP over side QF in the small right triangle FGQ. So repeat again. We derive the side LP in the big triangle over side JQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of this big semicircle, that is equal to 2, over GQ. GQ is the radius of this small semicircle, that is equal to 1, and it is equals to PF. PF in total equals to 2 plus 1, that is 4, plus x. So PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So, in conclusion, we should find out that 2 equals to 4 plus x over 1 plus x. Here we will multiply this equation by 1 plus x, and we get that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. So here we subtract x from this equation, and we get that here we have 2x minus x is x, so in total, this side of the equation we have x plus 2, that is equals to 4. Here we subtract 2 from this equation, and finally we get that x equals to 4 minus 2, that is 2. So we should find out that the length of this line segment CF that is equals to x is equals to 2 units. So I write it down. X equals to 2 units in its length. In the next step, we prove that the right big triangle, triangle ADF, is similar to this right small triangle, triangle ECF. So I'll write it down. The right big triangle, triangle ADF is similar to this right small triangle, triangle ECF. So why the big right triangle ADF is similar to the this right small triangle ECF? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually this is angle ADF. In the big right triangle ADF, and it is equal to this angle, that is actually angle ECF. In the small right triangle ECF. So I repeat again, we actually found out that angle ADF in the big right triangle ADF equals to angle ECF in the small right triangle ECF. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle, angle alpha, as it belongs to the right small triangle ECF, it will be defined as angle EFC. So repeat again. this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle DAF. In the big right angle ADF, and it is equal to this angle. This is actually angle CEF. This one right angle EFC. So repeat again, we actually found out that angle DAF in the big right angle ADF equals to angle CEF in the small right angle ECF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the three angles in the big right angle ADF are correspondingly equal to all the three angles in this small right angle ECF. And therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. So if we found out that the right big triangle ADF is similar, this is the same of similar to the right small triangle ECF according to angle similarity rule. And from the fact that the right big triangle ADF is similar to this right small triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AED, the big right triangle ADF, over side EC in the small right triangle EFC, equals to side DF in the big right triangle AFD over side CF in the small right triangle EFC. So I repeat again. We derive that side AD in the big triangle over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 units over EC. EC is the missing side, so we will leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6. And 6 plus 2 is 8. So in total DF equals to 8 over CF. CF is 2. So in conclusion, I have found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So I have found out that 3 over EC equals to 4. Here we multiply this equation by EC. So we get that 3 equals to 4 times EC. Here we divide this equation by 4. And finally we get that the missing side EC equals to either 3/4 or 0.75 units. So write it down. I found out that this is the missing side EC, and it is equal to either 3/4 or 0.75 units. So what is this? Here EC equals to 0.75 units in its length. What is the length of side BC over the angle ABCD? according to the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. AD is 3, therefore BC must be also equal to 3 units in its length. So I write it down, BC equals to 3 units in its length. What is the length of the missing line segment BE? From the drawing it is very easy to see that BE equals to BC minus CC. Again, BE equals to BC minus CC. So I write it down, BE equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. EC is 0.75. So in total, BE equals to 3 minus 0.75. That is 2.25. In conclusion, we have found out that the length of this line segment VE is equals to 2.25 units. What is the length of side AB of rectangle ABCD? According to the same rule that states that the opposite sides of a rectangle are equal to each other, so in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC equals to 6, and therefore the opposite side AB must also equal to 6 units in its length. So in the next step, I'll copy the right green triangle ABE in a new page, and we'll implement the Pythagoras theorem on this right green triangle, triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right green triangle ABE, the cubic of the original drawing. According to the Pythagoras theorem, in this right triangle, triangle ABE, AE square, that is the square of the hypotenuse, must be equal to AB square plus BE square. The hypotenuse AE is the missing side, so we will leave it as it is. So AE square equals to AB square. AB 6, therefore AB square is 6 square, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 square. That is actually equals to 5.0625. So in total, we found out that AE square equals to 36 plus 5.0625. So AE square equals to 36 plus 5.0625 equals to 41.0625. Here we take a root out of this equation and finally get that AE the line segment that we're looking for, AE equals to the square root of 41.0625. The square root of 41.0625 equals to 6.408 units. And that is the answer to the question. So repeat again, we should find out that the length of this line segment AE is equal to 6.408 units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. We know that side AED equals to 4 units in its length. In addition, inside this rectangle ABCD, we have those two semicircles. The radius of this big semicircle equals to 2 units in its length. The radius of this small semicircle is equal to 1 unit. Again, our mission is to find out the length of this line segment AE. So, first of all, we know that all the angles in any rectangle, all the 4 angles, those 4 angles are all right angles. Okay. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point as point P. We defined the center of this small semicircle, this point as point Q. Likewise, we define the touching point of these two semicircles, this point as point S. We define the point of tendency of tangent AE with this big semicircle, this point as point L. And finally, we define the point of tendency of tangent AE with this small semicircle, this point as point G. In the next step, we did a construction. That is to say, we extended line segment AE inside DC of this rectangle ABCD by a straight line until they touch each other. This is their touching point. We defined their touching point, this point that is their touching point as point F. So we know that DC is one side of rectangle ABCD and therefore it is absolutely a straight line. Then by doing the construction, we extended side DC by a straight line. When we extend a straight line by a straight line, the result must be a straight line. Therefore DF must be a straight line. So if we focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees. According to rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right small triangle ECF, we define this angle EFC as alpha. So in the right small triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furnace angle must be equal to 90 degrees minus alpha according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. So here we have PD equals to PS. They are both the area of this big semicircle, therefore each of them is equal to 2 units. Likewise, QS equals to QC. They are both the area of this small semicircle, therefore each of them is equal to 1 unit. We define the length of line segment CF as X. So here we have the radius PL of this big semicircle is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If A is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, the radius QG, is known to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is known to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If A is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. In the next step, we proved that actually, before that, we have in the right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees times alpha, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees times alpha. In the next step, we proved that the right big triangle LPF is similar to this right small triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that the angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees times alpha, therefore they are equal to each other. So if we prove that all the triangles in the big right triangle LPF are correspondingly equal to all the triangles in the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rules. So repeat again, we shall found out that the right big triangle LPF is similar to the right small triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side LP in the big right triangle LPF over side GQ in the small right triangle GFQ equals to side PF in the big right triangle LPF over side QF in the small right triangle GFQ. So repeat again. We will derive that side LP in the big triangle or side GQ in the small triangle equals to side side PF in the big triangle or side QF in the small triangle. LP is the radius of this big semicircle, that is equals to 2 over GQ. GQ equals to 1, and it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x over CF. CF over QF. QF equals to, in total to 1 plus x. So in conclusion, we have found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and we have found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation and found out that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation. So in this side of the equation we have 2x minus x is x, so in total we have x plus 2. And the other side of the equation we have only with 4. So in total we should find out that x plus 2 equals to 4. Here we subtracted 2 from this equation and finally found out that x equals to 4 minus 2, that is 2. So this is the line segment CF that is equal to x is equal to 2 units. So in the next step we proved that the right big triangle ADF is similar to this right small triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we proved that all the triangles in the big right triangle ADF are correspondingly equal to all the triangles in this small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So again, I should have found out that the right big triangle ADF is similar to the right small triangle ECF according to angle similarity rule. And from the fact that the right big triangle ADF is similar to this right small triangle ECF, we will derive that the following relationship exists between their sides. we will derive that side AED in the big triangle over side EC in the small triangle equals to sine DF in the big triangle over side CF in the small triangle. So repeat again. We derive that side AD in the big right triangle ADF over side EC in the small right triangle ECF equals to side DF in the big right triangle ADF over CF, the small right triangle ECF. AD equals to 3 over EC. EC is the missing side, so we will leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6, plus 2, 6 plus 2 is 8. So in total DF equals to 8 over CF. CF equals to 2. So in conclusion, we shall find out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so in total we shall find out that 3 over EC equals to 4. Here we multiply this equation by EC, and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4, and finally found out that the missing side EC equals to either 3/4 or 0.75 units. So this is the missing side EC, it is equals to either 3/4 or 0.75 units. What is the length of side BC of rectangle ABCD? According to the rule that the opposite sides of a rectangle are equal to each other, we will get that side AD must be equal, in the rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. Here BC is 3. What is the length of the missing line segment BE? From the drawing it is very easy to see that BE equals to BC minus EC. Again, BE equals to BC minus EC. So BE equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25 units. So here, the length of this line segment BE is 2.25 units. What is the length of side AEB of rectangle ABCD? According to the same rule that states that the opposite sides of rectangle are equal to each other, we get that in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2 plus 1 plus 1, that is in total 6. And therefore the opposite side AB must be also equal to 6 units in its length. In the next step, I copied this right triangle ABE in a new page, and we implemented the Pythagoras theorem in this right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So okay, this is the right triangle ABE that I got from the original drawing. This right triangle ABE, here by PT, is the version for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle ABE, AE square equals to AB square plus BE square. AE is the missing side, so we leave it as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 square, that is 5.0625. So in total, AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in conclusion, we found out that AE square equals to 41.0625. Here we took a root out of this equation and finally found out that the missing line segment AE is equals to the square root of 41.0625. That is actually equals to 6.408 units. Repeat again, I shall find out that the length of this line segment AE is equals to 6.408 units. Okay, thank you very much.